Okay, so let's have a look at this where the student is hydrolyzing two different haloalkanes, iodopropane and 1-bromopropane. So he's refluxing them with sodium hydroxide. Okay, so let's have a look at the question. Outline the mechanism for this hydrolysis of 1-iodopropane. So curly arrows. Okay, so it should be pretty straightforward. First thing you're going to do is make sure you pop your arrows on. I'm going to just zoom in on this. So I'm going to draw it like this. So then you can draw the delta positive and the delta negative. You've got your hydroxide, which is the nucleophile. So that is going to attack that positive center. So that means that for a moment, this carbon in the center will be making 1, 2, 3, 4, 5 bonds, which can't happen. So this bond is going to break because it's the weakest, and those electrons will both jump off onto that. And then you're going to get your CH3, CH2, CH2OH, which is propanol, and you'll have I- displaced into the solution. State the name of this type of mechanism. Well, because you started off with a nucleophile, it's nucleophilic, and because this has been substituted for this, it is substitution. Explain why 1-iodopropane is hydrolyzed faster than 1-bromopropane. The bond enthalpy is lower. Than the carbon. So bond enthalpy, you can think of it as just bond strength. So next question. Halogenoalkanes undergo nucleophilic substitution with ammonia to form amines. And they contain the NH2 group. Oh, so if we're reacting with NH3, they get the NH2 group. So there's another hydrogen atom gone walkabout somewhere. And they give you an example here. So you can just sort of substitute in the new molecule, because they're saying iodoethane is reacted with ammonia. So iodoethane is ethane with an iodine on it. So you've got CH3, CH2. There we are. And it reacts with 2 ammonias. So we can copy that. It's the same pattern. It'll happen the same every time. And so our final formula will be CH3, CH2, NH2. That's an amine called ethanamine. And what's happened is the other NH3 molecule has picked up remember one of the hydrogens from the ammonia has gone missing. It's picked up that to form NH4, which we know has got a positive charge. That's the ammonium ion, and that will bond with the iodine, which has been displaced. We know, or iodide, I should say, which is I-. So you can show the charges like that, just to show that it's ionic or not. That's what you get. Okay, next part of the question. I seem to have chopped off the top. Essentially, the reaction that we just looked at happens in 2 stages. And so it says this is the first stage. So complete the mechanism. Well, all we need to do is show the incoming nucleophile, NH3. I'm even going to draw the lone pair on top of the nitrogen. And you should show the delta positive, delta negative. So that is going to attack the delta positive carbon, causing that bond to break. And so the NH3 is joined on here. Okay, so it's bonds on there, and the Br- has been kicked out into the solution. Okay, so there's a second step as well by which you form your final products, but we won't concern ourselves with that for the moment. Okay, this next one, bit of an apology to make for this, because this part of the question is we don't need to talk about this. Okay, on the old course, we used to have to talk about different types of halogenoalkanes, primary, secondary, tertiary, and we will talk about those, but we don't need to know how they affect hydrolysis anymore. Okay, so this student is trying to hydrolyze 6 halogenoalkanes. Here they are. Those are the 6. Okay, so adding some ethanol, a few drops of the halogenoalkane, and they're warming it to 50. So they're adding aqueous silver nitrate. Anytime you see aqueous silver nitrate, it's because they're testing for the halide ions. Remember, silver nitrate tests for Cl minus, you get white precipitate, Br minus, cream, I minus, you get a yellow precipitate. So that's what silver nitrate is used to test for. And the time taken for the precipitate to form is recorded in the results table. So when the precipitate is formed, that means that the halide, the chlorine or the bromine or the iodine, has been kicked off into solution, and it will react immediately with the silver nitrate. And they do it at 2 different temperatures. They do it once at 50 and once at 60. Okay, so describe and explain the factors that affect the rate of hydrolysis. Okay, so firstly, if we look at the chlorine, okay, the chlorine at both temperatures takes the longest, 243 and 121. So I would say the chloride, remember, don't say chlorine because it's not an element. Chloride is the ion. The chloride containing halogenoalkane, I'm just going to shorten it there, takes the longest to hydrolyze. Now let's see which one is the quickest. Okay, it appears to be the iodine containing. So the iodide containing HA takes the longest, takes the shortest time to hydrolyze. So you've described, and now we need to explain. Okay, why is this? This is because the Ci bond enthalpy is lower than the Cl bond enthalpy. In fact, the CCl bond enthalpy is, I don't even know if it appears to, but that's very quick. I've never got it to work in the lab. I've never got the white precipitate. It just takes forever. Okay, so let's talk about the temperature of the hydrolysis. Well, if you compare all the temperatures at 60 degrees, the temperature is, the time is much lower. So at a higher temperature, at a higher T, particles have more energy. Therefore, there will be more successful collisions. What's going on here? More successful collisions, and therefore a higher rate of reaction. Okay, any words to those effect, that's how I would have approached it, but the main thing that I want you to know is that it is the bond enthalpy that is the main determining factor. It's not the dipole. I mean, let's see, the halogen and the halogenoalkanes. You may have mentioned the dipole here. You could have said, CCl dipole is bigger than the Ci dipole. Okay, something to note that they will have a dipole, a larger dipole on for this one, and it's easy to think, oh well, my nucleophile is going to attack that one much more strongly. This bond will be broken straight away, but it's not. It's the strength of the bond that is the determining factor. Okay, final question then. Compounds B and C are halogenoalkanes. They can both be hydrolyzed with potassium hydroxide. Describe and explain the hydrolysis of B and C. Okay, so I love it when they give you these little bullet points, because then you can use them to guide your answer. So one equation, including the structure of the organic product. So the organic product is the carbon containing. I'm going to draw them both. So one equation. So it doesn't matter which one you choose. I'll choose the one on the left. So there's your BR. So remember, you've got to put your dipoles on. Delta positive, delta negative. Now, I normally leave my hydrogens off, but there we go. Now they've been hydrolyzed with potassium hydroxide. So it's the hydroxide, the OH minus, that's going to be doing the work here. So OH minus, that's going to attack that positive carbon. That bond's going to break. So you're going to get the nucleophilic substitution. And that bromide, has been kicked off into solution. So draw the equation. Done that. The reaction mechanism, well, I've done that as well in one swoop. The type of bond fission that occurs. Well, bond fission is bond breaking. So it is heterolytic, isn't it? Heterolytic bond fission. There we go. And also I would say that that we are looking at nucleophilic substitution. The reason for the difference in the rate of hydrolysis, it doesn't give you any information, so you can display that you know what you're talking about here. You say the sorry, I'll do it this way. The bromopropane will be hydrolyzed more quickly than the chloropropane, as it has a lower bond enthalpy. Okay, so I mean, clear and well organized. I've probably lost a QER mark there, but I want to get the just the information across at the minute. I'm not too focused on crafting a perfect answer. I'm just interested in you understanding the chemistry. Okay, so heterolytic bond fission, we should know from when we did the work on free radicals and all that. Nucleophilic substitution, hopefully we know that by now. You can draw this is the mechanism, and well, it's the mechanism and the equation in one. And yeah, so there we go. I hope you found that useful.